This section of the cardiovascular system chapter on the vasculature will consider the dynamics of blood flow and what controls it. An important point about what we're looking at here is the concept of fluid dynamics, what moves liquids and gases around within our body. And we're going to start looking at that here with blood flow. We're going to revisit the idea when we get to the respiratory system. We're going to consider what affects blood flow. Now, this section is going to have some mathematical representations of the idea, which hopefully will help define it a little bit better. I'm not going to be asking you to solve equations based on this mathematics. It's just to help define the process a little bit better. Blood flow is dependent on several factors. The equation that we see here runs through what they all are. The important ones I want to point out are the difference in pressure. The blood is going to flow from high pressure to low pressure. The representation of the radius here is getting at how wide the blood vessels are. Blood vessels can dilate and contract, and that affects blood flow. Viscosity of the blood is just talking about how thick or watery it is, and that can have an effect too. And then lambda is the length of the blood vessel. The longer the distance the blood has to travel through from when it's pumped out of the heart to when it returns to the heart is going to affect blood flow. One of the reasons why obesity is a risk factor for cardiovascular disease is simply because more tissue requires more blood vessels, and therefore it's going to make the heart work harder to get that blood around the body. We can boil down some of the scary parts of that equation here, which isn't necessarily any less scary, but by putting them all together here, we can kind of get rid of them and just think of them in one conceptual framework, and that's resistance. Now, resistance is essentially a force working against blood flow, and it's dependent on a few concepts that are expressed in that equation. There's viscosity and length of the vessels, as well as the diameter of the vessels. And that's all represented here. The thing looks kind of like an N, that's viscosity. The upside down Y, or lambda, is length. And then pi r to the fourth is the expression of diameter and area that fits in with this. By taking these values in a particular instance, we can get to what the resistance is. Resistance is essentially the friction of the blood moving through the system as components like blood cells and water molecules and whatever not interact with the wall of the blood vessel, and that friction is going to slow down blood flow a little bit. As resistance is higher, blood flow is lower, and as resistance is lower, blood flow is higher. The power to the fourth, represented in the denominator here, shows that there's a pretty significant change in resistance on blood flow. If resistance goes up by a factor of 1, blood flow will go down by a factor of 16, if I'm calculating that correctly. So we can play with blood vessel diameter, for example, and make huge changes in blood flow from small changes in diameter and resistance. And that's the basis of a lot of what we have to control blood flow. The important aspects of the equation I just showed you can be boiled down really to just this. Blood flow is equal to the ratio between the difference in pressure over the resistance. Now, I described the difference in pressure before. That's just what's pushing the blood through, coming ultimately from the beating heart. Resistance really ties up a lot of the different things in that previous equation, length, diameter, the constant pi, viscosity, into a force working against blood flow. I often depict this just as friction. If you're trying to walk across the room and you don't lift your feet and you just drag them along, it's going to be harder to walk. Picking up your feet is going to do a better job of getting you across the room. That's essentially what resistance is. It can largely be attributed to the friction of the components of blood, red blood cells and those sorts of things, hitting the sides of the blood vessels. So that's sort of the friction aspect of it. It's a bit more complicated than that, but that's a simple way to think about it. And you can boil this equation down to basically when the difference in pressure goes up, blood flow goes up. When resistance goes up, blood flow goes down. So, to understand blood flow a little bit, consider this. The flow of water along a river is representative of blood flow. It's not a perfect simile because we're only talking about, kind of a half circle riverbed as opposed to the entire enclosed blood vessel. But the wider a river is, the deeper a river is, the faster the water will flow. So this is a picture of the Connecticut River, just to have a visual to represent this. And it's a very wide river and it moves quite quickly. I need to complete this visual, take a picture of a smaller river and just suggest that. But you can kind of imagine, maybe a creek somewhere. The water does not move that fast at all. You could be swept away in the Connecticut River. You can easily cross through a creek without any worry about the water doing anything to you. And that's sort of a representation of the diameter and blood flow relationship. It's not a perfect example, but it might get you thinking about what's going on a little bit in the blood vessels. These 4 graphs represent important aspects of what's controlling blood flow in the circulatory system. Now, before we look at them individually, I want to point out that along the y-axis of each of these, there's representation of the vessels that blood moves through. We start with elastic arteries, which would be something like the aorta, then muscular arteries, which is most everything else, down to arterioles, and then capillaries, and then venules, and then veins. I don't quite know why they put the vena cava separately from veins, because it really is just a vein, but we see all of those. First, we have a graph showing vessel diameter. This is an average diameter across the various types of vessels, starting with elastic arteries, which essentially is getting at the aorta, which is about 2.5 centimeters in diameter. And then the diameter goes down as we go into smaller and smaller vessels, understandably, until capillaries are practically at 0 on this scale. They're really going to be about 10 micrometers or 8 micrometers in diameter at that point. And then things go back up through the veins until we get to the vena cava, which is going to be even wider than the aorta that we see at the beginning of the graph. This graph shows the total cross-sectional area of all of the vessels at that level of circulation. Now, cross-sectional area is a little bit different than diameter, but it's still using the same basic data. The cross-section of the aorta is going to be based on a 2.5 millimeter diameter, which would be pi times 1.25 squared. And then as you go into higher and higher cross-sectional areas, the vessels are actually getting narrower, but more and more vessels are going to add up to a greater cross-sectional area across all of those vessels. And we see that the greatest cross-sectional area across all the vessels is actually in capillaries. There's so many capillaries. Even though their diameter is practically 0, they add up across everything to make for a huge cross-sectional area. And then that area drops down again as we go into fewer and fewer veins and finally into the single vena cava. Consider this representation for total cross-sectional area. One vessel with the diameter of 2.5 centimeters will give us an area of about 4.9 centimeters squared, whereas 100 vessels with a tenth of that diameter are going to individually give us 100th of the area. 100 of them together will give us the same cross-sectional area. And really, from one aorta out to muscular arteries of a 1/4 of a centimeter diameter, we're probably going from one vessel up to thousands and thousands of vessels. So the cross-sectional area is going to go way up, even though the diameter of individual vessels is going way down. Here we see the average blood pressure dropping off steadily from the aorta down back to the vena cava. Now, the numbers here aren't precise, but it gives a good idea, and the pressure is really just built up from the contraction of the left ventricle. And that pressure is enough to push blood along all that distance with a little bit of pressure behind it, even when it gets back to the heart at the end. This table demonstrates where all of the blood is found throughout the circulatory system. We're really mostly concerned here with the systemic circulation, which is what the previous figure just laid out pressure-wise. Within that, 64%, 2/3 of the blood, is actually in the venous side of circulation. And as the pressure's going down, the blood's not moving through quite as fast. The veins are able to expand and sort of keep that excess blood in there. We'll learn later on in regulation how that excess blood is available to compensate for changes in blood volume very quickly. As the pressure on the venous side has dropped, being so far away from the heart, there are a couple of ways to try to help keep that blood moving through the system as well as possible. One of those is called the muscular pump, which is a passive way that veins take advantage of skeletal muscle activity to help push blood through the veins. And this is mostly found in the lower extremities. Consider a vein here that has two valves, and between those two valves there's a certain volume of blood that's been pumped up this far. When you're walking, for instance, if these are the muscles of the calf, those muscles, when they contract, they get shorter, the bellies also get wider. They're going to squeeze in on that region of the vein that's passing through that muscle. The pressure built up in that little area will push the blood through one valve. It can't go the other direction because valves won't let things go backwards, ideally. That'll move the blood on up. Now, if there were a third picture here that kind of showed what happens when the muscles relax in the next frame, we'd see that blood from below can sort of be pulled up into that vacant area. By ejecting the blood out of that region after the muscles contract, the pressure in there is going to be lower than the pressure below the lower valve. And so that's going to help the blood move up into that space. And so that pump kind of works to move the blood up out of the legs. This can be very important, especially if you don't get up and move around too often, sitting at a desk, or if you're on an airplane or a car ride or something like that. To actually move your legs around, ideally get up and walk around, but if not, in the footwell of the car, move your legs around a little bit so you get some muscle contraction that'll help push blood out of the veins. I just said that previous slide doesn't quite show the accurate representation of the average blood pressure through the system, and this is a better representation of that. First off, in the arterial side of things, there's going to be a variation in the pressure between when the heart's contracting and when the heart's relaxed, which is what we call the systolic pressure and the diastolic pressure. Now, you're commonly familiar with hearing about the blood pressure being 120/80, for instance, and that 120 is the systolic pressure and the 80 is a diastolic pressure. So really what's happening is that there's a variation between those two, that range. But if we want to talk about the average blood pressure, that's what we call the mean arterial pressure. And that's calculated roughly as an average, except that it's weighted slightly to the diastolic side because the heart is relaxed for longer than it's contracting during the heartbeat. And so for 120/80, instead of a straight average of 100, it really would be at about 93.3 as a mean arterial pressure, which is what the gray line here is suggesting. But then that flows directly into a constant pressure that we see coming out of arterioles through capillaries and into venules and veins. Now, you don't want a variation in pressure in the capillaries because they have very thin walls and you don't want force being put on the pressure on the walls on a regular basis. So everything sort of collapses down to a common line at that point. And then, of course, in the veins, it's going to stay that way because it can't go back to having a pulse pressure within it. That's what this figure represents. Just a more accurate representation of the previous figure. Finally, here we see the velocity of blood flow, the actual movement of the blood through the whole system. It starts off moving quite fast out of the heart thanks to the high pressure. It slows way down as it comes to the capillaries, which is partly due to the increase in resistance as we get to narrower and narrower vessels. But it doesn't completely bottom out, so the blood's moving through the capillaries. And then as it moves into the venous side of return, we see an increase in the velocity. And this has to do with the drop-off in the resistance as the vessels start to get wider and wider. And that's going to help to return the blood back to the heart, even though there's no pressure increase at that point. Consider this question. When you feel that you've reached an answer, hit the next button to go into the next slide, which will reveal the correct answer. While there are more than just vessel diameter that go into it, resistance is effectively just the opposite of that. As vessel diameter increases, resistance decreases, or as vessel diameter decreases, resistance increases. And the point of this question is really to get at the fact that when we're regulating blood pressure and blood flow, we're usually concentrating on maintaining vessel diameter. We're usually concentrating on the changes in vessel diameter, vasoconstriction and vasodilation. And that gives us the change in resistance and a change in blood flow.